All right. Good afternoon. People in Zoom, can you see, can you see me? And can you see the notes? Okay, so let me see here. Okay, so first thing I'd like to do today, I'd like to talk about the assignment. So the assignment is now uploaded in Canvas and it's due. So there are different dates for the assignment. Um, First date is coming up March 27th, that's after the break. This is where I need you to, by that time, I need you to confirm the problem statement with me. And so you need to write the problem statement and the model by that date. And then you start working on, you should do this, you should finish this way before 27. So if you, try to do this as soon as possible so that you have time to work on. So you need to do derivation and also simulation, software simulation, and optionally hardware. So what's the assignment? The main goal of the assignment is to use optimal control or the principle of optimal control to serve a real community need safely and intelligently. Okay, so basically what you need to do is you need to use the various principles that we study in this class, whether the Ponteriagal minimum principle, the LQR, optimization in general, or reinforcement learning, MPC, to solve a problem. If there are two ingredients that need to be included in your assignment to get full credit. First one is mathematical derivation, and second one is simulation. It's up to you to use whatever software you are comfortable with, whether it's Python, MATLAB, C, language, or whatever. And I'm going to talk about the hardware in a minute. So obviously, we would like to get practice on applying the principles that we study in class to solve a real-world problem. And we also want to get practice in implementing the controller to solve a problem and get practice with software. Okay, so this is the learning objectives of the assignment. And of course, another objective is to solve a real-world problem and get experience with hardware if possible, hardware implementation. So when it comes to applications, it's up to you. So if you are working already on a project that involves optimization or optimal control principles, feel free to use that project. Or if you worked on a project in the past, you just need to make sure that you show understanding of the principles involved. So that's option number one. Okay, so if it's something that you're already working on, or if you would like to consult with your advisor, then that's option number one. Option number two, you do research, literature research, find a suitable paper, preferably journal paper, and take that as your benchmark or as your base, and you could reproduce the results on the paper. And of course, if you go beyond that, you'll get extra credits. But you need to confirm the paper with me before, by the due date, March 27th. The third option, I gave you some examples here. First one is, and this is also related to, so the first one is to use indoor micro drone to do scouting in an indoor area. So you can scan a building for dangerous materials and return safely to base. And for this is the first option that I stated here, because we have the hardware in the lab, in the drones lab. So I have Master of Engineering students, groups of students who are working with these autonomous drones. These are small drones that, so you can have a leg up in terms of setting up these drones. You just need to write the code and apply it to the microprocessor in the drone. And I have some students who can help with that, who can help in the implementation part. So so this is one option. You can use this in any, it doesn't have to be surveying. You can come up with any problem formulation. You can solve time optimal control. You can solve fuel optimal control, or a combination of both. You can solve constrained control. You can solve unconstrained control, right? And so this is an option that you can do with the hardware. It's up to you. There are other, I'm not going to read every other option I have here in the document, but there's also another option that is related to, so there are virtual simulation environments widely available, free in the internet, where you can simulate in 3D hardware instruments like a drone, for example, or a land robotic vehicle, or even a humanoid robot. So you can treat that it's like an avatar, it's like a 3D implementation of your code. So you can do that. So you, instead of and that will be regarded as a hardware implementation. Okay. So by simulation, let me go back one step. So by simulation, I mean, show me the trajectories, right? The time series trajectory. That's what I mean by simulation. Show me how the states go from point A to point B. What's the time? Just show me figures. That's simulation. But hardware, and I include here 3D simulation as part of the hardware, is an optional step. The derivation is the same as what we did in the class. So you need to show the conditions of optimality, and you can also use reinforcement learning. And also, so there are some topics that I'm going to cover in the coming lectures. So for example, dynamic programming is a topic that is related to the implementation of optimal control. So when it comes to implementation, this is why you have to be, when it comes to implementing the controller in hardware, implementing a switching control is not always easy. So you have to consider different options. Okay, and as the time progresses, I'll talk more about these implementation issues. Any question up to this point? Okay, so here in the simulation, I would like to see obviously the system dynamics. So for example, I would like to see how this position evolves over time, velocity evolves over time, or whatever the state of the system is. I'd like to see the control effort and whether the control is within constraints or not. If the problem you're considering is constrained. If you are considering noise, I'd like to see what happens if you apply noise to the system. And that is something that I would expect if you consider MPC, model predictive control. One of the nice things about model predictive control that I think I forgot to mention is that it can work with linear time varying systems and linear time invariant systems. Because all it needs in every iteration, in every optimization step, is the prediction. So as long as you know the model, it doesn't matter whether it's LTR or LTC, okay? Because you're getting the prediction in every optimization step. Second, it can be adaptive to external disturbances. So if you apply disturbance like wind gust on the drone, okay, then because you are measuring the state at every time and then you are taking that as an initial point, right, there is a correction action inherent in the MPC. This is why it's widely popular, right, because it can correct itself as optimization evolves. So if you are considering MPC, I would expect that you show what happens if there is disturbance on the system or noise. And of course, you need also to show performance metrics, right? Time, energy, all these things. What happens if you are minimizing energy? Show me that you really minimized energy, okay? One way to do it is to calculate the cost function, right? Calculate the cost function. And of course, the best way to do it is to compare with a regular controller or baseline controller like a PID or something, right? And yeah, so these are the expectations. And yes, go ahead.
In which basis that we do a comparison with the other controllers?
What's that?
In which basis or in which categories we do a comparison?
Yeah, comparison is if you are minimizing time, right? For example, apply PID controller, see if you minimize time, apply your controller, of course your controller, because it's optimal, time optimal, it should lead to less time to achieve the objective. So for example, if you are considering moving from point A to point B, okay, you can do that in PID by taking the point B as a tracking signal, as a signal that you need to track. So, so you can define the error between the desired final state and the actual state. And the PID is going to make that error equal to 0. But of course, it's going to take some time to do that. Time optimal, because there is a bang action is going to happen, then you would expect less time achieved. So by March 27, I need you guys to send me the problem statement. I need you to send it to me as soon as possible so that you can start working on the project as soon as possible, okay? But for sure, no later than March 27. Objectives, whether there are constraints, and the chosen method, the method that you would like to work on, right? Yeah, and the community need that you're going to serve. Like in about one page, you can do it in Canvas, but for this delivery, you can also do it by email if you want. Okay, email I think is faster. And then the final requirement is a technical report and a presentation, right? So a report that summarizes your derivation and results, and final presentation in front of class. So we'll have, I think, final presentation date April 24. Sorry, May 4. May 4 is the final presentation in class. Each one will have approximately maybe 15 minutes, okay, to present your result in front of class, and also you need to explain your method, okay? You are encouraged to consider hybrid approaches also if you want, you're encouraged to, as I said, work on current research problems. That's okay too. It doesn't have to be a well-established solution. It can also be as part of research. That's okay. Right. So if you decide to work on the drones, let me know. I can facilitate the, can give you the hardware. You can have some time to train on it. I will organize with my other students to give you a tutorial or something, okay? You can use your own hardware. If you are in Blacksburg, you can also consult with some of the labs in Blacksburg. You can also do that in Blacksburg. All right, any question? Any final question about the assignment? So this is worth 10% of the course, okay? All right, I'm going to upload homework number 3 very soon, hopefully before next lecture. So stay tuned for that. All right, so now let me go back to lecture, I believe, 8 and 9. This is lecture 8. So this is what we did last time. Let me recap that very quickly, right? So last time we considered the case when the final state is general. It could be, it's not like a point. It could be a surface. It could be a plane, right? Or it could be the whole plane of real numbers. And T1 is free. And if the subset S1 is the whole plane, then we say that the final state could be anything, okay? So it's free, we don't care, okay? And okay, so the cost function is this, and the control is constrained, okay? The regularity assumptions are always there, right? We assume that almost everything is smooth, except the Hamiltonian with respect to U, okay? So the key idea here is to define the key, what we call the k-dimensional manifold, right? And use that as if it's a constraint. Okay, so it's actually a constraint, right? Because we want to steer the final state, right, on this plane. Okay, so that's the idea. And what's this plane? This plane is we write the constraints as equality constraints as nonlinear functions of the state that is part of this subset. Okay, and of course we assume that we define these functions to be smooth functions, and also we define them in such a way that their gradient with respect to x are linearly independent. So the Pontryagin minimum principal conditions are the same. The dynamics of this system satisfy this equation as the gradient of h with respect to p, the costate, and the costate differential equation is equal to minus the gradient of h with respect to x, and this is the Hamiltonian. And the only thing that is different to what we did before is now, so x, right? This is the optimal final state at t is equal to 1. That's that point there, okay? And this is the function that, that this point belongs to. It turns out that the condition that we need is known as the transversality condition or the orthogonality condition. And that is this condition here, which is the costate, the optimal costate at T1 transpose times x minus x star of T1 is equal to 0, right? For all x that belong to this manifold. So this is the manifold, and this is the case when n is equal to 2. So here, this is a 2-dimensional manifold. So we have this manifold, okay? And in that manifold, this condition is satisfied. And what is this manifold? How we define it exactly? We define it as the gradient of g with respect to x, right? Which is that one, right? And times x minus x of t1 is equal to 0. So that is that vector there. Okay, so so the idea here is that so this is a summary of special case 2. This is the case that we just considered, right? When x of t1 is free, and this is the case when S1 belongs to the whole space, right? Then the final state is going to be free, and the final co-state is going to be equal to 0. Why the final state is equal to 0? Because, you know, because in that case, the manifold is going to be the whole space. And because of that, then this is the only one that is going to satisfy this equation here. Okay? And if x1 belongs to a subset of R, right, then this is what we need to satisfy. And so this is an example that shows that in this case, it's the same as the example before, except that x2 now at t1 is free, x1 at t1 is 0, and t1 is free, so it's a time optimal control. Okay, so in this case here, there is one boundary condition that's missing in order to solve the optimality conditions, right? We have 1, 2, 3, and we need the fourth one. Okay, so the fourth one comes from the transversality condition, and in that case, the first thing here is that because I have x1, so this is the S1, right? This is S1, okay? And because, you know, if x1 is free and x2 is free, then P is going to be equal to 0, right? But here, this is S1, which is a subset of R, okay? So this is the constraint, this is what's going to define the manifold. So the manifold, so we're going to define G1 as x1 of t1 is equal to 0. So that's part of S1. So S1 is all x1 that belongs to R2 such that x1 of t1 is equal to 0. Okay? And if you take the gradient with respect to x, for this x1, that would be 1 and 0, right? And then you define the manifold. So that's the manifold. The manifold is that gradient, okay? Sorry, not the gradient, it's the transpose of that, right? So if this is nabla G1, this is dG1 over dx, that's the transpose of that. So that would be a row vector 1 and 0 times something that should be equal to 0. That's our definition of that manifold, right? This is the manifold here, this one. So what is that thing that if we multiply by 1 and 0, that will be equal to 0, and that would be a vector of 0 and something. We don't care about that thing. Start, okay? Right, that thing actually is what we are going to use to, that's the tangent, okay? So this is the tangent, so M is the tangent, right? And yeah, so now we have this vector here, right? And that vector is the span of this vector here, right? So what is the perpendicular vector to this vector? In mathematical sense, it's what is P transpose, or P of T1 transpose times that vector is equal to 0. From here, we can see immediately that P star of T1 should be a star and 0, okay? Which immediately gives you the boundary condition that you want, which is P2 of T1 is equal to 0, right? And that's it. Now we solve it like before, except that now with this condition, but everything is the same. And it turns out that if you do that, because of this condition here, this is the final it's a boundary condition. It's a terminal condition. So there will be no switching because P2, for this particular case, U is equal to minus sine P2. We solved this before, right? And because P2 star of T1 is the final time, is equal to 0, there will be no switching. So we start from whatever we start from here, all right? And then we'll end up with this one. And that is, so you can see that this problem, so P2 here, if it depends on where you start, if x1 is positive or negative. So if x1 is positive, then you apply obviously minus U is equal to -1 because you want to take x1 to 0. Okay, so you do that, and because there is no switching, and x2 is free, it can be anything, right? And that's what's going to happen. And if x1 is negative, you apply U is positive, and that will take x1 up to 0, and x2 can be anything on the y-axis here. Okay, so that's the control strategy. That's the time optimal control strategy. All right. All right. Any question about this? Okay, so now let me go to today's topic. Sure. So today it's time-dependent systems and cost. All right, so in this case here, what happens if the system explicitly depends on T, right? And the cost explicitly depends on T, right? So T appears explicitly both either in the cost or in the system dynamics. We call these types of systems time-varying systems. And to solve an optimal control for these types of system, there's a trick that one can do, which is to consider time as an extended state. So you extend the state. So we are, of course, in the conventional dimension that we use in this class is that the dimension of the system is n. Okay, so if we extend it by 1, then the extended state will be x of n plus 1 is equal to t. Okay, and obviously if you differentiate this one with respect to time, so you have x dot of n x dot n plus 1 is equal to 1. Okay, so that's the differentiation with respect to time of this equation here. So if you put everything together in a vector, we have x and x of n plus 1. We call that a vector xe. Okay, differentiate xe, so you'll have x dot and x dot n plus 1, and x dot we know that's f, and x dot n plus 1 that's 1. Right? We call that vector field function fe. The initial, so this is the extended system dynamics now, right? What are the boundary conditions for this system now, right? We need the boundary conditions, right? The boundary conditions are the initial states, which are x naught and t naught, which are known. The final state, right, are x of t1, which is given, and it belongs to a subset S1. Okay, so this is the general case, right? Remember, special case 2 is the general case of special x1, right? Of special case 1. So x1 belongs to S1, and T1 belongs to R. Okay, so so in this case here, we're going to use the special case 2, the method that we explained in special case 2 to deal with this case here, right? Now, if you define or redefine the loss function as part of that includes the argument x of n plus 1, we call that LE. And if you let U star be the optimal control and X star be the corresponding optimal trajectory, right? Then the optimal trajectory is X star and T. So T is part of the optimal trajectory now, okay? And necessary conditions for the extended problem are going to be governed also by the co-state. So in this case here, because we extended the dimension by 1, of course, the co-state will also be extended by 1. So we have P and Pn plus 1. Now, if we write the extended Hamiltonian, so the extended Hamiltonian is Le plus Pe transpose Fe. Okay. Now, I can also write, so Xn plus 1 is nothing but T. So that's that. So Le is the same as Lxu and T. Okay. And because F dot, sorry, Xe dot, the last one is 1, right? Then I can write this as P transpose F plus Pn plus 1 times 1, okay? Which is the derivative of, this is the last part of Xe dot, okay? That's that. So I can, that's the last part of E, okay? So I can write it in this way here. Now, if you look, this is nothing but the normal definition of H, except that now we have an extra argument that's T, right? Plus Pn plus 1. Okay? Now, necessary conditions, of course, this is the main optimality condition of the Pinter-Yagan minimum principle, right? The key here, this is the key. We want to ensure that H extended, Hamiltonian extended, where the arguments are Xe star, Pe star, U star, always for all U is less than or equal to the extended Hamiltonian Xe star, Pe star, U. Meaning, right, if you take the Hamiltonian, if you vary U, right, then U star is going to be the minimum, right? So we say that the Hamiltonian is globally minimized with respect to U. So this is the main optimality condition by Pinter-Yagan minimum principle, right? Now, obviously, Pn plus 1, which is equal to Pn plus 1 is not related, it's not independent of U, okay? It's not going to be dependent on U, so it's independent of U. So in that case, we can write, so if we want to minimize HE, right, because this is independent of U, right, this term is independent of U, right, then if we want to minimize HE, we need to minimize H. That's the idea here, right? So we need this. So we need this for all U. Okay, so now, what are the optimality conditions? Remember, PMP, Pinter-Yagan minimum principle, typically has 3 optimality conditions, right? First one is the dynamics, which is governed by this equation, right? The gradient of the Hamiltonian with respect to P is equal to X dot, right? And so I can write it in this way, and immediately you can see that we have the original. So from there, you know, so now I'm applying the conditions on HE, right? But as you can see, immediately you can see that you know, for this condition is equivalent. So notice I'm using the if and only if sign here. This is the equivalent sign. This is equivalent to this, and this is equivalent to that. Okay, so which is the same as the original dynamics, condition for the original dynamics. Similarly, the condition, second condition for the co-state, right? Yeah, there is, I think there is a mistake here. And there is a typo here.
X.
Yeah, it should be enable X, XE, not PE. Yeah, this should be X minus XE. Yeah. Okay, so, second condition, P dot is equal to minus the gradient of H with respect to X. So there is a typo here. So P dot is equal to minus the gradient of H with respect to X, and P dot N plus 1 is equal to minus dH over dt, right? Why? Because you can see it from here. You can see it from here. Okay, so yeah, that's it. So these are the two conditions that are from there, and there is also a minus here that is missing. Okay. Boundary conditions. So the boundary conditions, the initial conditions are here, which is the same as the one that we are given, and XE at the final time belongs to the subset S1 times R, which immediately we can see that T1 is free and X of T1 is equal belongs to S1. Okay, so because we are dealing with the special case 2, okay, we need the extended co-state at T1 because now there is only one condition that's missing, right? So PE star of T1 must be transversal to S1 times R, okay? And because the last one, T1 is free, right, which is Pn plus 1, is free if you go back to the table and actually in the previous lecture, right? If you have the final state to be free, then this is the condition that we have that satisfies the transversality. And then what remains to be satisfied is the original co-state P at T1 must be transversal to S1. Okay, so we need that. This is we now have it. Okay, and those will finish the conditions that we need. Okay, so in that case, this equation is well defined now, right? Pn plus 1 dot is equal to minus dH over dt with its boundary conditions, and we need the other boundary conditions for the other P's, the other P co-states. Okay, now so let me now continue. Okay, so you'll see where I'm going with this one here. So there will be like a closed form condition for this one here. So let me now take this one. Consider Pn plus 1. Okay, you can integrate both sides from this equation. Okay, you can integrate both sides, and knowing that this is a boundary condition. Okay, so you can, even though T1 is the final time, you can integrate this reverse in time. You can assume that as if this is T1 as if it's an initial time. So when you reverse the time, you reverse the minus, the sign of the integral. So meaning if you have an integral from 0 to T1 of something, right? If you reverse the intervals of the integration, instead of 0 to T1, T1 to 0, you multiply the integral by a negative sign. That's exactly what's going on here. We are going to T, so we're going to start from T and end at T1. Okay, and so this is as if, as I mentioned, I'm considering T1 as if it's an initial time. Okay, and as if this is like the initial boundary condition, and this is the differential equation. Okay, forget about the physical meaning of T1 for a second now. Okay, so I can write the integration of this equation, right? Either from T1 to T with a negative sign, or t to t1 with a negative times negative, that would be positive sign. The negative sign is coming from here. Do you all see that? All right, so now I have this one, okay? And I need you to bear with me here to see the final result of this. So, so we know that, we know that the extended Hamiltonian at the optimal trajectory, at the optimal, this is the third condition, okay, for the HE is equal to 0 for all time. We know that the extended Hamiltonian can be written as the original Hamiltonian with a t as an extra argument plus Pn plus 1 star is equal to 0. So this is equivalent. This is equivalent to that. I just wrote this as this one, and the equal sign to 0 here. This is the third optimality condition. Okay. Now I can take this to the other side, Pn plus 1 to the other side. So I have h of x star, p star, u star, and t is equal to minus Pn plus 1. And what's Pn plus 1? That's what Pn plus 1. So substitute by Pn plus 1 here. Okay. Now, if you do the chain rule for differentiation for h, so you differentiate h with respect to time, right? So that is going to be dh over dx times x star, x dot, at everything at the optimal trajectory point, plus dh over, remember, h is a function of x, p, u, and t. So the chain rule, I need to take care of all these four arguments. So I have dh over dx times dx over dt, right? Plus dh over dp times p dot, dp over dt or p dot, plus dh over du times du over dt, plus dh over dt times dt over dt, which is 1. Okay, so this is just nothing but the chain rule application. And I can now replace x dot by the gradient of h with respect to p from the optimality condition. Similarly, I can replace p dot by the negative of the gradient of h with respect to x, okay? And at dh over du, right, in theory is, and here I'm assuming h is differentiable with respect to u, right? That's equal to 0. Because this is where what optimality is, right? The derivative of the Hamiltonian with respect to u is equal to 0. If you go back to the variational approach, that's the main condition that we use there. So here there's an implicit assumption, just for the theory, that h is differentiable with respect to u. So that term will go to 0, okay? Now I am left with these three terms, right? Now, also from the optimality conditions, this term is equal to that term. So these two terms will cancel each other, and we'll end up with h dot is equal to dh over dt. Okay, so now you can replace dh over dt by h dot. Okay, so now I have this. Now I have, at the end, I have this. H of x, p, u, and t is equal to minus integration from t to t1 h dot. Okay, now notice that here this is t, okay, and this is a limited integral. So if you use the calculus fundamental theorem, right, this is nothing but if the solution of this, right, take the minus outside, this is h, substitute by t1, minus h, substitute by t. The minus times the minus will be plus. If you take it to the other side, that will cancel out. And you will end up with h at T1 is equal to 0. All right, and that is the condition that this is the third condition that needs to be satisfied. So in summary, okay, to solve this problem that of the time varying problem, okay, you need three optimality conditions that we all know, right? The first two optimality conditions are the regular ones. The x dot is the gradient of h with respect to p, and p dot P dot is equal to, again, this is P dot, this is wrong. P dot is equal to negative gradient of x, of h with respect to x. So these are the two regular optimality conditions. We need now boundary conditions with these two conditions. The boundary conditions are the initial states, right? And the finals. What are the final states? The final states are this, right? Which is the general case. So this is special case 2, right? So the final case, one of them is free and the other belongs to S1, right? For that, we need P of T1 to be transversal to S1. This is the original P, and the extra P is equal to 0. Okay, so these are two optimality conditions, the general like before, but with this extra piece of information here, okay? We need the third condition, the third optimality condition. The third optimality condition, if you go through the analysis that I did, is what's in the box here, right? Which is similar to the third optimality condition for the general case, except that H is 0 only at T1, not for all T. So remember, see here, it's H is equal to 0, not for all T, because in this case here, H explicitly depends on T. Okay, so before H does not explicitly depend on T. So before we have H of X star P star U star is equal to 0. Now for this time varying system, right, the third optimality condition, we need, when you plug in T is equal to T1, this is the only case when H is equal to 0. In addition, of course, of the optimality optimal trajectories. So I need you now to pay attention to the differences between the regular case and the time varying case. Remember, we are considering here a time varying case, where the system is dependent on time, or the cost, the cost is dependent on time. Okay, so very similar conditions to before with some extra conditions. So more information can be found in the book, especially Theorem 5.9 of Athens and Fal. Any question? Yes.
And this only works for when U is when the Hamiltonian is differentiable by U, right? Like if
it's implicitly assumed. Yes, yes. And in this case here, yeah, it's implicitly assumed. And I think also, so here we did not also consider the constraints. So we can safely assume that it's differentiable with respect to U. Yeah. So if H is not differentiable with U, then the math is going to be much more complex. Yeah.
Can we use the variational approach since there is no constraints and also differentiable?
Yeah. This is essentially I'm using the variational approach here. Yeah. Yes. So because there's no constraints. Okay. Now let me just consider now another special case. This is the case when T1 is given. So we want to solve the optimal problem in specific time. Okay. So obviously it's not a time optimal control anymore. It's an energy optimal control, or it could be a mix, but not the time optimal control. So T1 is given. So to solve this problem, you can again sit in a similar approach as to the time varying case. So this one here, the system is time invariant, okay? But T1 is given. So what you can do is you can extend the state again by 1 and define the extra state as T, okay? And then you have x is equal to x and x n plus 1. In this case, x of T1, the original x, belongs to a set, or which is a subset of R, right? And x, or the extra state, obviously the final, state, in this case here is T1. So basically what we want, because of this, so we need P star to be transversal to S1, okay? And because Pn1 plus 1 star needs this, so this is the case, this is special case 1 for this part here. This is a special case 1 where the final state is given. So when the final state is given, right, we don't need the P for that. Pn plus 1 star is free, we don't need it. So this is special case 1, right? So it's now, in this case here, it's very interesting. It's a mix of special 1 and special 2. Special case 1 and special case 2, right? So for this part, for the P star, it's a special case 2. We need P of star T1 is transversal to S1. Whereas for this part, because it's given, specifically like a point, right? Then we don't need the P for that, right? We don't need a P because we can use we can use the boundary condition for X, we can use that boundary condition, okay? So that's fine. So in this case, it can be shown that in this case, there is no third condition of the minimum principle. You can solve the problem with 2 boundary conditions, not two optimality conditions, I mean. Okay, so there is no need for the third optimality condition. And for more information, you can see theorem 5.10 of Athens and Fadl. Okay, any question, guys? All right, so now let me consider an example, just an extra example. All right, so in this case, I'm going to consider the problem of control of production and consumption. So this is a well-known problem in economy, okay, and finance. And so this is, you can find this problem in page 5 to 6 and page 51 to 53 of the textbook that where the author starts with E. Okay, it's in the syllabus. So what is this problem? This problem, consider a factory with X of T is equal to the amount of output produced at time t.
Professor,
Yes,
do you mind sharing the screen that you're writing on?
I thought it. Okay, thank you. Sorry about that.
Yeah, it's better. Thank you.
Thank you. All right, so X here is the amount of output produced at time t, and U of t, which is the control or the optimal decision that we would like to design, is equal to the fraction of output reinvested at time t. Okay, so basically, we have a factory produces a product, and we want to know how much of the output we need to reinvest. Okay, so at time t. So we consume 1 minus u times x and reinvest u times x. So u here is a fraction less than or equal to 1, larger than or equal to 0. So for example, if we want to decide to reinvest 90% of the production of the factory, then u is going to be 0.9. So you multiply 0.9 by x, the output of the factory, and that is the amount that is going to be reinvested. Okay. So what are the dynamics? So we need the dynamics. So the dynamics of x of t, right? The output, how is the output going to be produced? So the output is going to change over time according to dynamics, according to differential equation, right? So x are modeled by x dot of t is equal to k is a constant, u of t, x of t. So this is the dynamics of the system. Okay. All right, so the initial state obviously is going to be positive, and k is a constant, typically positive, which represents the growth rate of our investment So basically, we want to maximize the total consumption of the output. right? So i.e. we want, so i.e. meaning the total consumption of the output is, so we want to maximize this one. From 0 to T1, 1 minus U of T times X of T with respect to T, right? And T1 is free in this case. We don't care about it. Right? We don't care when this finishes. All right, so in this case, I can write J as minus integration from 0 to T1, 1 minus U of T, X of T with respect to time. Why I multiply by minus here? Right, this is the cost function that I want to maximize. Okay, but I wrote my cost function as a negative of that.
Just to maximize the negative,
Yeah, which means
minimize.
right? Which we can then do whatever we learned in class, right? So yeah, so we multiply by a negative because now we can design or find the optimal U that minimizes J. Okay, which in turn will maximize this one. So for the sake of simplicity, let's assume that K is equal to 1, the constant K. So in that case, the dynamics are given by Ux. Okay. And by the way, this system is not a time invariant system. So it's a time varying system, but it does not explicitly depend on T. All right, it implicitly depends on, so it's not an LTI system, but for the purpose of optimal control, it does not explicitly depend on T. Okay. All right, so the cost L is equal to that part, which is U minus let me write this because it's a minus, so I have to be careful. So in this case here, J can be written as from 0 to T1, U minus 1, X with respect to time, right? So L is equal to U minus 1, X, and F is equal to Ux. And the Hamiltonian is equal to L, which is U minus 1 times X plus P transpose F. Because the system is first order here, right? System is first order, so there's no P transpose. It's going to be P U X. Okay, so let me combine things. So I have minus X plus 1 plus P U X. Okay. So, because the system, it's like, so let me do this here on the side. So you have the system X dot is equal to Ux, right? So I can, this is dx over dt, right? This is equal to dx over dt. So take dt to the other side. Then you have dx over, and take x to the other side over x is equal to u dt. Now integrate both sides. So if you integrate both sides, you have ln x is equal to the integration from 0 to t u with respect to tau plus a constant. And so you can finish this by taking e to both sides, will be equal to e to the power of integration from 0 to t u of tau with respect to tau times x naught. Okay. So if you take e both sides, this is what you will get. So this is the equation for that will give you a prediction of x in the future. So this will give you an insight, given u, of course. So for any given u, right, this is the equation that governs how x behaves in the future. All right, so x of t is equal to e to the power of integration from 0 to t u of tau with respect to tau times x naught, right? We know that x naught is positive, so this is positive. And obviously the exponential is also positive, right? So the whole thing is going to be, x is always going to be positive, which makes sense. It's a production, okay? So there's no negative production. And this is for all time. Okay. So here, Pontryagin minimum principle, right? Then we need to focus on this one here. We need to focus on, because x is always positive, right? So this is the term that we need to worry about. You know, we're going to do it like by inspection now, because we want to satisfy the constraints. And because x is always positive, then what's going to minimize h is this term, and in particular, you know, the coefficient 1 plus p. Okay, so if 1 plus p is positive, right, then the minimum u we can get is what? Is 0. The constraints on u are 0 and 1. Okay, so the minimum u that we will get is 0. Okay, and if 1 plus p is negative,
1.
Then 1. Then u star is equal to 1. Okay, so that's going to be actually so because x of t is positive for all t larger than or equal to 0, and h is equal to minus x plus 1 minus 1 plus p ux, okay, then u is equal, then not u, then f 1 plus p star of t positive u star, the optimal u of t is equal to 0, it's the minimum, and f 1 plus p star of t negative. Okay, and switching happens obviously when 1 is equal to when 1 plus p star, or when p star is equal to minus 1. Okay, and negative, that's u star of t is equal to 1, and I can combine both. 0 when p star of t larger than minus 1, and 1 when, so I need, this controller is based on observing the p dynamics, right? So we need to solve p and observe it, and that will govern how u is going to, is less than minus 1. Any question? Now, just to finish, we need of course, just to, because I didn't, I immediately jumped on H, right? But we need to finish this. We need to state the conditions of the optimality. So condition number 1, X dot is equal to UX. Condition number 2, P dot is equal to the negative gradient of H with respect to X, right? So that would be equal to negative P dot, negative the gradient of H with respect to X, that would be 1, right? Plus 1 plus P U. Okay. The initial conditions for X is given, right? Yeah, it should be given, right? So it's the initial production. So X naught is given, is positive. We need another initial condition with that is for P, right? So what is the initial condition for P? Not initial, boundary, I should say, boundary condition or the terminal condition for P. What do you think, guys?
What about X? Do you have the final state of X?
What's that?
Do you have the final state of X? Oh,
No, we don't. It's not given.
okay.
It's not given. Because actually that's what we want. We want to maximize the total consumption of the output. No, so it's not given. The final production output. Yes.
You know that P has to be, you have to be investing 0 right at the end state because you're going to be like consuming.
Okay.
Because you want to invest as you're going to, if it's like the bang bang switch,
Right.
right? You want to be investing the maximum amount until you
Right.
decide to start consuming.
Yes.
So then we know because of that, that at the terminal state, P has to be less than -1, right?
Yes.
So would that help us?
Yeah. So the correct answer P of T1 is equal to 0. Yes. But we need to know why. Okay. So let me write it down and let's think about it. Okay. And I'll continue discussion next lecture. So in this case here, P of T1 is equal to 0, right? And this is because I'm going to write it like this, but we are going to continue the discussion. X of T1 is free. Okay? X of T1 is free.
So
And the problem is free. We don't care about X of T1. The final production, we don't care about it. Okay? What we care about is we want to maximize the total consumption of the output, which is this one, which is different than X. Okay, but anyway, we don't care about final X. So, okay, I'm going to stop here. Okay, and hopefully I can continue next time. All right, thank you guys, and see you next time.
Thank you.
Thank you, Alessandro.